Good. Okay. So far, I was talking about one-dimensional systems, and for me personally, the motivation was really to try to better understand when people talk about using one-dimensional topological superconductors for quantum information processing, what is the physics behind that? Can we grasp some of the physics with non-interacting, non-superconducting setups? But now in the second talk, I would also like to use the one-dimensional model, the SSH model, to start with as a building block towards higher dimensions. So I will use a method which is often called dimensional extension to start from the one-dimensional system and try to project its properties to higher dimensions. And by this means, I'm planning to introduce adiabatic pumping in one-dimensional insulators. So in this case, the Hamiltonian will have two parameters, k and t. K is just the one-dimensional momentum or wave number, and t is going to be time. So I'm going to talk about systems where the Hamiltonian changes in time, and as a result, some pumping of electrons, such a pumping of charge is happening. And then if we have an understanding of the toy models of that physics, then it's very easy just to say that actually time, let's make the time ky. And that's sort of a mapping between one-dimensional and two-dimensional systems. So by this we will arrive to two-dimensional Chern insulators, where there is no time dependence, but these are two-dimensional materials with kx, ky momentum components. And the topological features seen in adiabatic pumping in 1D will directly appear in two-dimensional band insulators. And then the last step, I guess I won't have too much time for that, but the last step would be just to take Chern insulators, or two-dimensional topological two-dimensional time reversal symmetry broken insulators, Chern insulators, and just, let's say, take two of them, double them in a time reversal invariant way, and this construction procedure would give you quantum spin Hall insulators. So that would be the end of the talk. And again, I'm following the lecture notes. So this second lecture is based on these chapters in the book. Okay. So this is message number 3. If the bulk has non-trivial topology, then edge states provide quantized conductance. This is for two-dimensional Chern insulators. This is the bulk boundary correspondence for two-dimensional Chern insulators. So here actually the robust quantity which is predicted by theory and observed in experiments is actually an experimental feature. Okay, so I was saying that in SSH model is a nice toy model to introduce the concept of topological insulators, but I'm not sure that realistically anything protected can be seen in SSH type systems. But it's very different here because 2D Chern insulators do exist. Quantum Hall effect is the most prominent example. So this is one place which is one topic which is much more close to actual experiments. If I have time, I will also talk about some experiments into that direction. Okay, so this is the manifestation of bulk boundary correspondence for this particular situation, two-dimensional systems without any symmetry. Okay, and so to start, first I want to introduce adiabatic pumping and the topological properties of adiabatic pumping in one-dimensional solids, because that will lead to two-dimensional Chern insulators right away. So the key element in adiabatic pumping can be sort of introduced only using two sites. So this is adiabatic pumping using two sites. So the setup is shown here. I could say this is the same charge qubit as before. So I have just a single electron sitting either on the left side or on the right side. So two sides, single electron. I assume that I'm always in the ground state. So when I say adiabatic, I mean very slow. I start, my initial state is a ground state, and also for the whole pumping procedure, I'm always in the instantaneous ground state of my Hamiltonian. So that's adiabatic. And then I have two control parameters. The hopping, V, that's a real quantity in this simple setting, and the on-site energy, U. Now I do introduce some different on-site energies for the two sites. One is called U, the second is minus U. And thereby, the Hamiltonian looks like this. So it's 2 by 2 Hamiltonian. I have two-dimensional Hilbert space. On-site energies appear in the diagonal, and hopping appears in the off-diagonal. And my goal is to cook up a simple procedure when I can pump a single charge from one side to the other side. This is elementary, but nevertheless, let me just go through this. So this is my initial configuration. I have one electron on the left and 0 on the right, and I want to end up pumping a single charge to the right, to the other dot, the right dot. And I'm illustrating the scheme here. So here what I plot is the time dependence of these two parameters, U and V. So purple is U, the on-site energy, and V is the hopping. So initially, okay, I try to sort of dance what's going on. So initially, what we have is that the on-site energy is low in one of the dots and high in the other one, and there's no hopping. So I could show that by saying that energies are different and they are far apart, so there's no hopping. Okay, and in the ground state is this one, so I have the electron here. Now what happens if I follow this procedure which is drawn here? In the first step, I make this hopping larger. So that means that I bring the two dots closer to each other. I make this hopping larger, but still there is a large energy gap, on-site energy difference. But they are closer now, so that means that some of the charge from here went up here a little bit, okay, a little bit of charge. Then in the next step, if you look at the graph, then what I do, I keep this V, the black is remaining over there, but I change the U, I go from -1 to +1. So I have this situation and I bring them to resonance and then move on. When I'm at resonance, I have 1/2 distribution of charges. When I move on, I have more here than here. And then I separate them again, that's the last step. And that's how I end up with 0, 1. Okay, so this procedure is a very simple one. It's just illustrating what I do with my control parameters, on-site energy and hopping, in order to pump adiabatically, because I'm always in the ground state, one electron from the left side to the right side. And this intermediate situation, which is plotted here, is just a situation when the two energies, on-site energies, are the same. U is 0, so here, and close to each other because V is large. That's why I have this 1/2. Okay, so this protocol pumps a single charge from one side to the other. Now we extend this to one-dimensional solids. So the basic model for this is just almost as simple as the SSH model, but also includes on-site energies. So adiabatic pumping in the lattice, I will take the example of a time-dependent so-called Rice-Mealy model. This is, as I said, essentially the same as the SSH model. I have A sublattice, B sublattice, a hopping between them, V, within the unit cell, and neighboring unit cell, it's W. So I have, instead of 2 parameters, I have now 3 parameters. I can also exemplify, okay, so this is the real space Hamiltonian, the same as SSH. The first 2 terms are just borrowed from SSH. And the last term is describing you an on-site energy difference. MA has U, and MB has -U on-site energy, okay? And now again, I can exemplify this with a 4-unit cell setup. This is the explicit form of the A-dimensional Hamiltonian. You have U minus U in the diagonals. Again, it will be useful to look at the momentum space Hamiltonian. And since it's still a 2x2 Hamiltonian, the momentum space Hamiltonian, I can write it out explicitly in terms of Pauli matrices. So as before, the SSH was this part, V plus W cosine K sigma X plus W sine K sigma Y. This was the SSH model, K-space Hamiltonian. And now I also have this on-site energy, which is just a sigma Z term in the Hamiltonian, in the K-dependent Hamiltonian. Again, I have 3 Pauli matrices, 3 coefficients, so I can form a 3-dimensional vector again. So now, this model is a model where I'm mapping the 1-dimensional brilliant zone, so that's the unit circle, I'm mapping to a 3-dimensional closed surface. Okay, so this is a bit more advanced because I have a 3rd dimension also. The vector is 3-dimensional, but this geometrical consideration is mapping between the unit circle as the brilliant zone and the 3-dimensional space is still working. So we expect that topology will be able to be invoked. Okay, and what do I mean by adiabatic pumping? So I mean that all these parameters of Hamiltonian, V, W, and U, they can be time dependent, but I want to be adiabatic. I want always to be in the ground state, so I do not allow the gap to close. So I say that I tune somehow my V, W, U, but I take care that the gap doesn't close at any point of time. So this D vector, which is just the energy, well, this is 2 times the magnitude of D vector is just the energy gap of the full system. That should always be bigger than 0. When I say pumping, I mean something periodic. So I mean that I assume a cyclic time dependence with some period T, capital T. And I look at slow pumping to remain adiabatic, so I look at the t goes to infinity limit. So this is how I sort of define adiabatic pumping after Thales, who discussed this scheme, I think, first in that paper. And then the question is that, okay, I do this is pumping, this I call pumping, but is it really a pumping? So am I pumping charge through any cross-section of this material? So this is the question I'm addressing here. How much charge is pumped through a cross-section? Let's see. So first I want to illustrate this with a very specific pumping protocol, and this is what we call a control freak pumping protocol. So a piece of psychology is now intruding, so maybe this is a technical term from psychology. I looked it up in my dictionary. Control freak, a person who feels an obsessive need to exercise control over themselves and others and to take command of any situation. Okay, so I guess I'm a control freak in some sense. So I get a paper from a student, usually I rewrite the whole thing, I figure out new notation, so I think that's sort of an example of a control freak. And I want to introduce you a control freak pumping protocol. And here control freak stands for, describing the fact that here, in a generic solid, my electrons are delocalized. So they're all over the place. But now I want to be a control freak in the sense that I want to have a structure where I know that in every moment of time, my electrons is localized on a single dimer. So that's what I mean by control freak, because I know if I know that in every moment of time my electronic eigenstates can be localized in a dimer, that means that I can follow how they evolve in time, so I can answer the question whether there is any pumping or not. Okay, so that's why I'm doing this control freak. I want to be very precise in knowing where my electron is. And I take this solid. So this is now the Rice-Melle model. I have 3 parameters. I have unit cells of 2 sides. I'm playing with the parameters. So here you see V. This is intra-cell hopping, W inter-cell hopping, and U is the on-site energy. And I'm starting, this is now just giving you a recipe how to modulate in time these parameters of the Hamiltonian in order to get something interesting. And I'm trying to explain what this interesting thing is. I'm looking at this position here, time equals 0, initial state. Can I use localized eigenstates? Well, let's see. My parameters are the following. I have W and U being 0, and V is finite. So only the intra-cell hopping is finite. So I have dimers, well-defined dimers in each unit cell. So I know that I can start the time evolution from a setup where I have an electron sitting in a unit cell. In the ground state, how is this electron distributed within the 2 sites in the unit cell? It's distributed 50-50 because my hopping is on. My V hopping, the black line, that's on, so there's a bonding in between them. So the bonding state is going to be the ground state. So this is my initial state, and I can follow what's happening to this state when I do this kind of modulation of the parameters. And again, so I would sort of dance what's happening. I will not do that. I'm just pointing out that I do in 4 steps. So in the first step at time equals 1/4, it's very easy to see that by this adiabatic pumping, I will pump this 1/2 charge onto the right dot, but still I know that my charge is localized in a single dimer. I move on. In the next step, I'm going to transfer 1/2 of this electron to this side there. That's happening in this situation, or this segment. And then in the last 2 parts, I pump this 1/2 charge to there, and then again I distribute this charge there. It's too easy to see that the ground state is really following this pattern. So that's why I call this a control freak pumping scheme. It's control freak because I always know where my electron is. And it's pumping cycle because I started from somewhere and this single charge went 1 unit cell to the right. Okay, so the observation I want to make is that I could easily cook up, just by understanding a 2-level system, I could cook up a protocol where in a 1-dimensional solid we can pump a single electron per cycle. Okay, so let's go back to this geometrical picture which I was sort of anticipating beforehand. So here I just repeat again Rice-Melle model, momentum space Hamiltonian, first 2 terms are the SSH model Hamiltonian, and then I add this on-site energy term. And that's how I get this decomposition with Pauli matrices. This D vector is just a 3-dimensional vector, has X, Y, and Z component. And let's visualize how this looks like. So I do have a cyclic modulation of parameters. So whatever I started with for V, W, and U, I'm ending up with the same values. So it's a cyclic thing, which means that actually I can think of my sort of pseudo-parameter space as being a two-dimensional torus, because I have a one-dimensional Brillouin zone, k goes from minus pi to pi, and I have time as my pseudo-dimension. From 0 to 1, my parameters are periodic in time. So when I start from 0, that's identical or equivalent to time capital T. So my sort of pseudo-parameter space is a two-dimensional torus. Torus because you would say it's a square, but actually the opposite edges of the square are identified with each other, so it's a torus. Okay, so what this Hamiltonian is doing me is it's giving me a map between some abstract torus, this is this KT Brillouin zone, and the three-dimensional space. So I can imagine, I can draw what is the image of my pseudo Brillouin zone, this two-dimensional Brillouin zone, in this three-dimensional space. Okay, and I'm doing this. So I'm just taking this scheme, and I'm just, I know that the x component of my D field is this one, the y component is this one, the z component is this one. I'm just drawing what is the image of my KT Brillouin zone in this three-dimensional space. And this is what you see. Let's try to identify what's what. So let's at least try to identify what is the point in the D space which corresponds to the initial time point. So here you have only V on, W and U are 0. So let's plug all these values here. So everything is 0 except V of t, that's 2. Okay, and the D vector has this form. So I have to plug in W equals 0, then cross it out, U equals 0, cross it out, and the only term is this one, V. And I'm tempted to draw circles as k, so I fix the time at 0, and I want to draw circles as k goes between minus pi and pi. So what is my circle, how does my circle look like when t is 0? All these terms are 0, so it's actually a circle with 0 radius, there is no k dependence. So actually this point, this is the point which is corresponding to the initial time point. So this is actually a circle, but it's a circle of 0 radius. And then if I start to turn on time, I follow what's happening to the circle, then for a while, as you see, for a while this W is still switched off, only this U is rising. Well, U is the Z component, so that's when I go from this point up to this point. Still, I'm drawing circles, but these circles have 0 radius because W is switched off. W is the radius of the circle. But then I move in that direction, and here at this point, up to this point, all my circles were just points. But up at this point, I'm starting to increase W. So where is this point in this graph? So W is starting to get increased here, right? When I start to increase W, that means I start to increase my circle radius. So that's where I go like this. So these are not real circles. So the gray lines are actually those circles which correspond to the Brillouin zone at a given point of time. And then if I go on in time, I get this largest circle, and I go down, and again I squeeze down into a single point and then come up back here. So this is a picture, this is an image of a torus, but it's a very sort of deformed image, a strange image, squeezed. So here the torus is very much squeezed, right? So here it looks like a segment of a torus, but here it doesn't, but it's very much squeezed. Okay, so I have a mapping from an abstract two-dimensional torus to an embedding in the three-dimensional space. So again, it's a fairly simple topological type of mapping where I can cook up a topological invariant. And in this case, in a generalization, if I take generalizations of this model, then the topological invariant is called the Chern number. I'm not introducing the Chern number in terms of Berry curvature, Berry connection, and so on. I'm just using this geometrical representation. The Chern number in this case can be 0 or 1 depending on whether my origin is inside the torus or it's outside of the torus. And okay, another way to phrase the same thing is this recipe. If you are interested in the topological invariant, then let's sit at d equals 0. Let's sit at the origin. Let's go to infinity from the origin along some straight line, for example, let's say upwards, and count the number of intersections with the torus. Okay, so that's I start here, I go up, I just intersect with the torus here, go down, go out. So that's 1. Again, if my origin is inside the torus, then that's 1. If it's outside, then it's 0. That would be my first naive argument. Of course, you could say that, well, let's take this recipe and go along dx. So I sit here, I start to go along dx, I cross once here, the border, but then I also cross here. So that's 2. So it's like it's not a topological invariant because it depends on how I look. But of course, the recipe contains implicitly that whenever you cross these torus, you should take into account whether you cross from the inside to the outside or from the outside to the inside. And that counts with different signs. Okay, so when I do this, I go to x direction. What I do cross it once. Then I come from the outside to the inside. Sorry, I come from the inside to the outside. But then when I cross this point, then that means that I actually first go in and then come out. So that's a +1 and -1, and I had to add up all this. Okay, so that's how this is topological invariant. That's how it makes sense to use this recipe as a counterpart for the Chern number. Okay, but the key point is that for this pumping, the observation is that the topological invariant of this torus is 1. So it's an interesting correspondence, right? Because it pumps 1 charge per cycle, and it has a topological invariant of 1. Okay, so again, this is some kind of a correspondence between the bulk and the bulk. So this pumping is also an effect in the bulk. Okay, let's see how this turns into a bulk boundary correspondence. So let's again do the same thing. We started from a bulk, but let's take a finite wire. How does control-free pumping work in a finite wire? So we take exactly the same pumping cycle as before, but with a finite wire, n equals 10 unit cells. And before looking at the graphs, we could speculate what happens in a finite wire, right? So we have seen that if I look at the bulk, now what happens in a cycle is that a single charge will move 1 unit cell to the right. If I now fill all my valence band with electrons, then what's going to happen to these electrons? Of course, in the middle, the electrons can be pumped 1 step per cycle. But what happens on the edge? So that's the question. So electrons cannot pile up at the edge, right? Because then sort of the quantum mechanics is unitary, so you cannot converge to a single attractor state. So there should be some kind of unitary time evolution. So the simple naive picture is that actually in the bulk the electrons are transmitted 1 unit cell per cycle, but in the edge they have to do something, and they cannot really do much. What they can do, they can go up to the conduction band, and if they are up in the conduction band, they can move left as pumping is going on. But to go up to the conduction band, you need a level which is connecting the valence band with the conduction band. Okay, and that's illustrated here. So what you see here is again just an exact diagonalization of a 10 unit cell Rice-Meller model, and what you see is the energy spectrum as a function of time. Okay, so when you start, we have seen that only the intra-cell hopping is switched on. It's a value of 2, so you have bonding, anti-bonding states at energy -2 and 2, and of course all these points are 10-fold degenerate because I have 20 states. And if I change time, all these degenerate states will move together. That's no surprise, because I was setting up my Hamiltonian in such a way that it always separates to individual dimers. And if I have this setting, that means that I have sort of flat bands. I don't have a dispersion of the bands, and that's why these lines are degenerate and there's no splitting. Okay, but as you see, when I arrive to this time point, there's going to be one state which is deviating from the other 9, and that indeed moves up. If I look at the wave function, it's totally focused or localized on the right edge. Also, in the same time, a state from the conduction band is coming to starting to come down. Again, I look at it; it's perfectly localized to the left edge. So, indeed, what I was trying to explain, it does work. It's what's happening. So that the electrons are sort of the bulk electrons. The electrons in the middle of the chain are pushed 1 unit cell in each cycle, but at the edge, there's nowhere to go for them, so they have to go to the conduction band. That's explicitly appearing in this plot, right? And also, you see that these states which are going from the valence band to the conduction band, these are localized states. And that's, again, reasonable. So it would be very surprising to see delocalized states in the gap. because this is a semiconductor, so in the gap there are no delocalized states. So if there are states connecting the two, they must live on the edge. All right.
But this is, yeah, so I'm a bit confused about this, because it's an edge that exists in time, in your time parameter space.
Yes. Yes, this is the time, and maybe I was not very precise. I'm describing a situation when I start with a completely filled valence band. So all my valence band states, all these 10 states are filled. And my question is, what is the time evolution of this state as I tune slowly this time variable, which is controlling the parameters of the Hamiltonian, V, W, and U, in the fashion I defined before. And my claim is that what happens is that you have 10 states, but at that point, one of the electrons filling those 10 states will start to go up to the conduction band in this sort of spatial fashion, that when it's going up, it's localized on the right edge, and the others will remain in the valence band. Okay. So this means that one electron is taken from the valence band to the conduction band per cycle.
Sorry.
Yeah.
If you continue.
Mm-hmm.
What happens then?
In this simple model, what happens, if you continue in this simple model, what happens is that this guy is going to end up there again in a fairly localized state. And then if you do another cycle, then another of these 9 will go up. So in this very simple model, in this control freak model, you pump up the whole thing to the conduction band. So the whole picture is like a conveyor belt, that you go to the right in the valence band, and then you go up to the conduction band and then move to the left, and the whole thing goes as a conveyor belt. But this changes when you go away from this control freak limit, because then all these states become delocalized. So then what happens is that you start from the Fermi sea, and then you can pump one electron to the conduction band, but that's going to come down already in the second cycle. So then you don't do this conveyor belt, only with one electron. So this is somehow the essence of what's happening in these situations. Okay. So now you see, this cycle pumps a single electron per cycle. We can associate a topological invariant, this Chern number, to this torus, which is embedded in the three-dimensional D space. That's also one. And we also see that one electron is going from the valence band to the conduction band. There is one edge state appearing in a certain period of time for this pumping cycle. So again, this sounds like a Bach boundary correspondence for the adiabatic pumping, because my topological invariant I calculated for the Bach is predicting the number of edge states appearing in the spectrum. Okay. And one can, of course, move away from the control freak limit. That's just important to keep track of the charge in a very simple fashion. One could go to, I'm just now taking the control freak cycle. This you've already seen, and I deform it in a sort of an adiabatic fashion, meaning that I can deform this to this without closing the gap. So that's what I mean by adiabatic fashion. I just deform this black line to this cosine type line. I deform this purple line to this sine, and then I deform this trapezoid line to this. This goes without closing the gap. I can also illustrate how the torus image of the KT torus looks in the D space. Again, this is a torus. This is now obviously a torus. It's much nicer torus than this one, and it encloses the origin. So it's a topological invariant is 1 again. Right, and of course I can also look at the spectrum of this non-control freak case, and what does that tell me? Well, I did a continuous deformation, so I was not closing the gap at all, but that implies that these edge states cannot be sort of dissolved. They cannot disappear, because I did a continuous transformation. The only way they could disappear is if they could hybridize here where they meet. But they cannot hybridize because they are located at different edges. They are far from each other. Okay, so that means if I do a continuous deformation, I start with the Hamiltonian where I have edge states, then I end up with the Hamiltonian which has edge states. Okay, so just by these continuous deformation arguments, I think it's pretty easy to conceive that this is a robust phenomenon. So indeed, it's a Bach boundary correspondence. Indeed, if you do the calculation for the Bach model, then that's going to predict what's happening in this pumping scheme for a finite lattice. Okay, so the continuous deformation can't change. None of these parameters, the topological invariant, edge number of edge states, number of pumped electrons, these are all remain the same under continuous deformations. Okay, and so basically I think that's the essence of 2D Chern insulators, even though I have not mentioned 2 dimensions, I was talking about 1 dimension and time as the two dimensions. It's very easy just to take the same models and promote time t to momentum ky. So from now on, instead of thinking about a single one-dimensional chain, we think about a ribbon. So in the x dimension we have a confinement, so we have edges, we have terminations.